Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello teacher, hello students. Welcome to today's lesson about integral calculus. We are going to begin to explore some of its mathematical applications. In the mathematical application, we will calculate the area of a region bounded by curves of continuous functions on a closed interval. We have a lot to learn today, so if you are ready, let us get started. We have already learned how to find the area of some regions under the graphs of a non-negative function when the definite integral was defined. Now, the application is a bit different. We will be calculating the area of a region bounded by curves of continuous functions. These functions are defined on a closed interval. Observe this graph of a function. We will use integrals to find the area of the bounded region. Let us designate the three separate areas as A1, A2, and A3 from left to right. First, we will plot the region below the axis. Since it is below the axis, the integral is negative. Specifically, it is the negative integral from 1 to 2 of x squared minus 3x plus 2 with respect to x. This equals negative x cubed over 3 minus 3x squared over 2 plus 2x restricted from 1 to 2. By substitution, this can be evaluated as 4 minus 23 over 6 or 1/6. Second, we can see that A1 and A3 are symmetrical curves. So, we plot their areas in much the same way. A1 is the integral from 0 to 1 of x squared minus 3x plus 2 with respect to x. And A3 is the integral from 2 to 3 of x squared minus 3x plus 2 with respect to x. Here are their respective solutions. As you can see, because they are symmetrical, they each have the same area, 5/6. To discover the total area of the region bounded by the curve, we simply add A1, A2, and A3. The sum is 11/6, which is our answer. Now, I will have you try to plot the area of this graphed function. Please find the total area of the region enclosed by the graphs of f of x equals x squared plus 4 and g of x equals 1. And the lines x equals 1 and x equals 3. Try your best to do this now, and I'll see you in a few minutes.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Did you manage to solve this tricky problem? Let us check the solution together. We need to find the integral from 1 to 3 of x squared plus 4 minus 1 with respect to x. This equals x cubed over 3 plus 3x, restricted from 1 to 3. This equals 9 plus 9 minus 1 over 3 plus 3, which equals 44 over 3. Did you find the same answer, students? If so, great. If not, please try the question again once the lesson has finished to find out where you made a misstep. We will explore this further now. Let us suppose that f and g are continuous functions on a coordinate plane. F of x is greater than g of x. The area bounded by the curves of y between the lines of x is communicated by this formula. Please make a note of it. Let us apply this principle for ourselves by finding the area of this region. It is enclosed by two curves that are described by these polynomials. Now we solve for x with the equation x squared minus x minus 6 equals x minus 3. We can simplify the equation to x squared minus 2x minus 3 equals 0, which can be factorized to x minus 3 times x plus 1 equals 0. Therefore, x equals 3 or negative 1. F of x is greater than or equal to g of x on the closed interval negative 1, 3. The next step is graphing our functions. Since we know that one function is a hyperbolic curve and the other is a straight line, the graph looks like this. Now we must find the area of the region. It is expressed by the integral from negative 1 to 3 of x minus 3 minus x squared minus x minus 6 with respect to x. This can be evaluated as the integral from negative 1 to 3 of negative x squared plus 2x plus 3 with regard to x. This equals x negative x cubed over 3 plus x squared plus 3x restricted from -1 to 3. We have almost finished. Substituting the two values of x, we are given an equation which simplifies to 9 minus 1 over 3 plus 1 minus 3, which equals 32 over 3. Now, I will ask you to solve a similar problem on your own, students. Please find the area defined by these functions. Get started right away.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. If you followed our formula and the three-step process, I hope you did not have too much trouble. 3x squared minus 4 equals 2x squared. Therefore, x squared minus 4 equals 0. So, x equals positive 2 or negative 2. This is the graph of our function. The area equals the integral from negative 2 to 2 of 2x squared minus 3x squared minus 4 with respect to x. Simplified, this equals the integral from negative 2 to 2 of 4 minus x squared with respect to x. The problem has become simple. For x minus x cubed over 3 restricted from negative 2 to 2. Therefore, the area is 32 over 3. Great work, everyone. That is all for this lesson, students. Today, we have learned how to calculate the area plotted by two bounded curves. This is the first mathematical application of integral calculus we have learned. In the next lesson, we will discuss plotting the volume of a revolution. Until then, thank you, teacher. Thank you, students.